Now, let's extend our skills for reading data frames from files. We'll use a comma-separated values file of sunspot observations collected from CILSO, the Sunspot Index and Long-Term Solar Observations. The entries date back to the 19th century with over 70,000 rows. The read_CSV function requires a string describing a file path as input. We read into a data frame called sunspots. Using the info method, we see the data frame has mostly integer or floating point entries. Notice the index of the data frame, the row labels, are of type range index, that is just integers. Let's use the accessor.ilog to view a slice of the middle of the data frame. We can now see some of the problems. The column headers don't make sense, and there are some perplexing -1 entries in one column. What's going on? First, the CSV file does not provide column labels in a header row. The column meanings can be gleaned from CILSO's website. Columns 0 through 2 give the Gregorian date. Column 3 is a decimal value of the date. Column 4 is the number of sunspots observed on that day. And column 5 indicates confidence in the measurement, 0 or 1. Second, the -1s in column 4 denote missing values. We'll need to take care of those. Finally, as written, the dates are awkward for computation, a common problem with CSV files. Let's tidy this up. Using header equals none prevents pandas from assuming the first line of the file gives column labels. Alternatively, an integer header argument gives the row number, indexed from 0, where column labels actually begin and the data begins. Notice now the columns and rows are assigned integers from 0 as labels. We can explicitly label the columns with the option names. We define a list of strings col names to label the columns properly. We can also read the -1 entries in the sunspots column as NaN, or not a number, sometimes called a null value. We do this with the NA_values keyword. We try NA_values equals quote -1 quote, but the sunspot column still has entries of -1. Looking at the original CSV file reveals the problem. There are space characters preceding -1s throughout column 4. Thus, we use NA_values equals quote space -1 quote, and it works. Notice the sunspot numbers are now floating point values and not integers. Several strings can represent invalid or missing values. To do so, we use a list of strings with NA values or a dictionary mapping column names to lists of strings. Note it is possible to use distinct patterns for null values in different columns using dictionaries. See the documentation for examples. Finally, we remember the year, month, and date columns can be loaded in a better way. The past dates keyword in read_CSV infers dates intelligently. We use a list of lists of column positions indexed from 0 to inform read_CSV which columns hold the dates. Sure enough, there's a new column of date times named year, month, day, amalgamating the 3 original columns. In fact, using the info method, we see year, month, day column has entries of type date time 64. We'll learn more about date times when studying time series. They're invaluable for many time-based computations. Also, the sunspots column has about 69,000 non-null entries. The data frame still lacks meaningful row labels as index. The year, month, day column can be assigned as a data frame index using the index attribute. Similarly, assigning date to the index's name attribute gives a more concise label. Notice we still have the year, month, day, and dec date columns. To get rid of them, we list the meaningful column names and extract them. The result is a more compact data frame with only the meaningful data. What if we want to share this new data frame with others? The sensible thing to do would be to export our compact data frame into a new CSV file. The method toCSV does the job for us. Like readCSV, the toCSV method has a host of options to fine-tune its behavior. We can even export to Excel using the toExcel method. Try some exercises now to practice loading and saving data frames. Data visualization is a primary tool in a working data scientist's toolbox. Let's see how to do it with pandas. For convenience, we import pandas as PD and matplotlib.pyplot as PLT. We load the Apple stock data into a data frame using readCSV. Notice we use the options parseDate equals true and indexCol equals date to force a datetime64 index. Again, we'll use these indexes a lot with time series shortly. Also observe entries in the volume column are significantly larger in magnitude than other columns. Now we assign close R by indexing Apple close, yielding a series, and applying the values method, yielding a NumPy array. Remember, the command plot can plot NumPy arrays or lists, and the command show must be executed to make the plot visible. This is the resulting plot of the stock close prices. Notice the horizontal axis of the plot corresponds to date indices of the array. We can actually plot pandas series directly. We assign close series from Apple as a series and call plot with close series as an argument. The result is a similar plot, but a bit nicer. The plot function automatically uses the series' datetime index to label the horizontal axis. An even nicer alternative is to use the pandas series plot method, that is, apply closeSeries.plot. The result is as before, but with even more formatting and the axis labels and the name on the axis, date, inferred from the index name. In fact, pandas data frames have a plot method just like pandas series. Calling apple.plot plots all of the columns of the data frame Apple on the same axis. Pandas plots each numerical column against the index and uses the column labels in the legend. However, on this scale, we can't see all 5 line plots because one is so much larger than all the others. We can produce a similar plot using plot.plot from the matplotlib using the data frame as argument. This implicitly draws all of the numeric columns of Apple against the index. The figure resembles the one plotted using the data frame method plot, but there is no legend and no title on the date axis. Again, the volume column dominates the other 5 curves and they cannot be seen on the same scale. To remedy that problem, draw the plot again and call yscale_log. This matplotlib function sets a logarithmic scale on the vertical axis. The legend still appears automatically, but now we can distinguish volumes on the order of 10 to the 7 from other price values on the order of 10 to the 2. Any matplotlib options can be used to customize a series or data frame figure. For instance, we can abstract the open and close series and plot them separately, specifying the colors, line styles, and legend labels. We zoomed the axis in to the year 2001 with the vertical scale from 0 to 100, and we explicitly place a legend. To find out more about matplotlib customization, see our course on data visualization in Python. Notice again, the horizontal date ticks are labeled for us cleanly. Finally, having drawn a figure, it's useful to be able to save it for future use. To obtain the preceding plot, we slice 4 columns and the rows corresponding to 2001 through 2004 inclusive from the Apple data frame. We'll learn more about time series splicing later. We generate a plot and apply the savefig method to preserve the plot. Savefig can infer the file format, for instance, PNG, JPEG, PDF, and others, from the suffix of the file name. Now it's your turn to make some fancy plots using pandas in the exercises.